postdoc at KTH in Robotics Perception and Learning Lab. And I mostly focus on applications of algorithms and machine learning to robotics and a little bit to natural sciences. That's what I'm going to talk about today. So in robotics and generally in many kind of applications, one basically will have a system that is evolving over time, so some kind of dynamical system. It's very important to have the notion of a state space. So basically it's a state of all possible states or configurations of a system that can be described as a topological space, speaking in mathematical terms. So in this example here, we have this very simple illustration. So we have a linkage that has 2 degrees of freedom. So it's just 2 angles, Q1 and Q2 on this image. And it's configuration space, so a space that fully represents all possible states in which the system, in this case the linkage, can be is this torus. And this notion of state space or configuration space is fundamental for formalizing various problems in robotics and molecular science, as we will see now. So when we talk about state representations, we can think of problems that vary between different application areas and that can be represented in different scales. So we can think about motion planning, for example, for a car or a fleet of autonomous cars, and in which case our planning scale is the size of a city, for example, so we measure it in meters. Or we can talk about molecules that move and interact with each other, or that try to penetrate some kind of porous membrane, and that their motion is basically restricted by this membrane. And in this case, we talk about really micro scale. And as we will see now, the concept of a state in this first example of a car, or in the example on the bottom of a molecule, is fundamental. So what do I mean by a state? In this case, if I talk about objects, rigid objects moving in 2D as a car, or 3D as a molecule, their state is just basically their position and orientation in the space. If I talk about deformable or articulated objects, as I will in the second part of my talk, we will have much more complexity because we will have much more degrees of freedom. But basically this concept of state and the space of states is really fundamental for formalizing various problems. So what kind of problems can we consider here? We can think of connectivity analysis as our first problem. And what we're trying to solve here, no matter if we work with a robotics problem or if we consider certain applications in molecular science, the question here is basically in this high-dimensional state space, so the space that incorporates all possible position and orientations for now for simplicity of an object or of a robot. The question is whether it can move from point A to point B while respecting certain constraints that exist in the system that are basically problem specific. So in the simplest kind of understanding of these constraints, we can just say that the rigid body is moving while trying to avoid collisions. So we have the parts of the space that represent collisions where our body collides with some obstacles. And the rest, basically the complement of this region, is what we call a free space. So the question here is whether there exists a path from point A to point B. And as we will see in this talk, this is a complex problem, mostly because when we talk about state spaces or configuration spaces of more or less complex systems that are not just a rigid body moving in a 2D space, this space is very high dimensional. And because it's high dimensional, it's difficult to represent computationally and it's difficult to analyze at connectivity. Another problem that kind of builds upon this connectivity analysis is the problem of planning. So now, assume that there exists a path from one state of the system to another. Then the question is, how do we plan this path? So how do we move from point A to point B? So it's this problem is kind of dual to the problem of connectivity analysis or path existence, because here we assume that we have a path and our goal is basically to find it. And our system can be anything starting from a mobile robot moving in some cluttered environment to, for example, a robotic arm that is manipulating some complex objects in a cluttered scene. So really, when we talk about finding a path here, it's not maybe literally just a geometric path, but it's a sequence of transformations that the system has to go through. Another problem that also naturally arises in this context in robotics is manipulation and grasping. So the question here is, if we now think about the state space of our object, so in this case it's this monitor, the question is, how do we safely grasp and manipulate this object without letting it fall on the floor? And in this case, we kind of restrict its mobility geometrically by putting the robotics arms around it, such that it cannot escape. And because it cannot escape, we can basically provably show, mathematically prove that this object is safely grasped. So all these problems, as we can see, they rely on basically connectivity analysis and path planning in complex state spaces. So what are the main challenges when we talk about state spaces and their representations? So as I mentioned before, one really big challenge is high dimensionality of the system. So when the more degrees of freedom your system has, the more complex the state space is and the more difficult it is to represent it computationally and basically do any kind of planning or search in it. Because as you add dimensions to your system, so as you allow your system to have more degrees of freedom, the complexity of the state space rises exponentially. So that is like one big challenge. Another challenge is that the state space is kind of a mathematical abstraction of the system. But in reality, we have to deal also with real-world challenges, such as perception and noisy sensory input. So normally when we talk about a robot operating in a space, it's basically knowledge or what it sees and feels comes from its sensors. So another kind of problem here is how to using this often noisy and incomplete sensory input, how to transform it into this mathematical abstraction and how to integrate it basically with our state space representation. And another problem is when we talk about the system that have really many degrees of freedom, how do we capture those that are really relevant for the task? Because maybe we don't need to model every single degree of freedom that the system has, but we want to focus instead on what is specifically relevant for the task that we have. And here it's important to find a balance basically between considering like the right amount of generality. So on the one hand, we don't want to kind of engineer our application that will work only for one task. But on the other hand, it's also important to find what is relevant for this family of tasks and how to define the family of tasks for which we can do something meaningful. Okay, so that's basically the main topic of my research. It's learning and designing state representations for robotics and as a side project for molecular sciences. And in the core of it is basically my background. It's a mixture of applied mathematics and computer science. So I borrow a lot of tools and concepts from fields like applied topology, computational geometry, and classical algorithm theory. And I combine them with machine learning methods because they provide high computational efficiency and robustness to noise and to incomplete data. And basically I use this mixture to represent state spaces in various areas such as autonomous systems, so it's robotics mostly, and molecular sciences. And so what is important here for me personally is to find this good balance between tools and concepts that we borrow from mathematics, so kind of like purely analytical approaches, and learning-based approaches that allow us to deal with real-world data. So on the one extreme, we can think of methods that are becoming increasingly popular now that are purely learning-based. So it's, on the one hand, it's very appealing to kind of say that you have a machine learning model that just solves the problems for you completely. But on the other hand, when you work with complex systems like robots, you soon will realize that you need to introduce some sort of domain knowledge and domain priors. Just because otherwise the problem becomes too complex and too data inefficient. And data is something that you really need to be mindful about in robotics applications because it's not readily available. Usually it's very expensive to collect data in this kind of applications. So for me personally, it's important to find a good way to represent states by basically using domain prior about the task that we know with the data that comes from the real world. So yeah, and in the rest of my talk, I will talk about how exactly and what kind of priors we can introduce using concepts from applied topology and computational geometry. So the first class of problems that I will consider is the questions of past non-existence and caging that I will explain in a few minutes in applications in robotics and chemistry. So, as I explained already before, the problem of analyzing path connectivity or finding, like answering to the question of whether there is a path or not from point A to point B is one of the important problems, in particular in robotics, when we basically want to understand whether our system can move from one point to another. Another kind of relevant and highly related problem that comes from robotic manipulation is that of safely grasping, or as we also say in robotics, caging objects. So why these problems are kind of dual to each other. So in the case of caging, when we want to restrict the mobility of this monitor here, we really want to understand whether there exists a path that leads our object from its initial position where its mobility is bounded by the robot arbitrarily far. So whether basically it can escape from the manipulators or not. And it's, as we can see, this problem is really dual to this problem of past non-existence, because here it's a more general question of whether an object can move from one configuration to another. And in chemistry, we also find an application of this problem that is basically related to the topic of molecular cages in organic chemistry. So in organic chemistry, we can think of geometric interactions between molecules and geometric properties of molecules that kind of define this interaction. So there exists a certain class of molecules that is called cages in organic chemistry. And it's basically this kind of molecule. So they're rather big and they have a cavity inside. So they have some kind of hollow structure. And these molecules can be used in applications like, for example, drug delivery, when you want to use this molecule to capture another small molecule and to basically immobilize it, just like in the previous case that we saw with the robotic manipulator and an object that the robot is trying to grasp. And in this kind of context, an interesting research question is to help chemists to find good pairs of molecules that can basically restrict each other's mobility. Because usually when a chemist works in a chemical lab, synthesis and testing of these pairs of molecules is a really challenging task. So it can take a long time and it's also quite expensive. So what we're trying to do here is to design an algorithm that will basically perform screening, computational screening of potential cage candidates, so candidates of this big molecules that can encapsulate smaller molecules, and the respective small molecules, and just see whether these pairs can form cages or not, so whether one can encapsulate another. And we have shown in our work that this problem and the problem of cage and past non-existence mathematically is basically equivalent. So we can use the same kind of algorithms that we developed to solve both of these problems. Here, it's quite an old work. So here we have taken a purely kind of mathematically inspired approach. So there was no kind of machine learning component yet. So what basically we did, we just like dealt with our state space explicitly, and we came up with a geometric algorithm that basically represents explicitly the state space, which allows us to analyze for each specific point in the space whether it is caged, so whether if the object is in this specific configuration, whether it can escape or not. And also to analyze whether there is a path between any arbitrary pair of points. So this paper that I'm citing here, it basically presents like fully computationally complete approach, and it has provable guarantees. Which is good because we only use concepts from computational geometry to formalize this problem. And on the kind of sad side, it's unfortunately quite computationally expensive. So what we basically do, we start with geometric representations of the object and the obstacles, whether it is a pair of molecules or it is a robot and an object that the robot is dealing with. And then we construct this full representation of the state space. And then we just query this representation to see whether there is a path or not between pairs of configurations. Okay, but as I said, the main challenge here really is high computational complexity of this approach. And unfortunately, if we approach it from a purely kind of analytical perspective, this is inevitable because, as I said, the complexity of the system grows exponentially when we add more degrees of freedom. So here we were working with 3D objects moving in 3D space. But if we allow any kind of additional flexibility to the object, so for example, if we assume that our object that the robot is working with is deformable, then the computational complexity will be even higher. So purely analytical approaches are not sufficient here to solve this problem completely. Yes, and we applied this algorithm to applied problems in different areas, like, as I mentioned, organic chemistry, robotic manipulation, and also self-driving cars and motion planning for self-driving cars. Okay, but what if now we want to generalize this problem a little bit and say that we allow partial cages? So that means that we don't want to fully restrict the mobility of the object anymore, but we just want to restrict it to a certain extent so that it's hard. It's basically difficult for the object to escape. And this problem becomes even more complex because now we introduce this kind of notion of flexibility of a cage. So we're not talking about full cages anymore, but we also talk about cages that can potentially be escaped. And in this case, we had to resort to deep learning approaches, and with my coworkers, we actually obtained an interesting result that shows that we can use a deep neural network to approximate computationally expensive but analytically kind of probably correct algorithm, and we can get pretty good results with just building a machine learning approximation of this algorithm. This way we can combine computational efficiency because the whole system now works in just milliseconds with really this complex geometric notion of interaction between these different objects with complex shapes. Okay, but what if now our objects are not just rigid like we were considering before, but what if they're articulated or even, let's say, fully, like completely deformable like clothes? Well, in this case, we have really no hope to explicitly represent their configuration space because it's going to be infinitely many-dimensional. And here the question becomes, how do we even parameterize the state of the system? How do we even say in kind of what a configuration is for the system? So for example, if you take this shirt that you want to fold, as in the example here in the slide, it's really hard to kind of mathematically describe in what is a sufficient state representation for this object, because it's very flexible. It has many wrinkles that are not relevant at all for the task of folding, for example. And things get even worse when we assume that we have to deal directly with sensory data. So we start with kind of an image of the scene instead of fully geometrically specified pose and shape of the shirt. So in the work that I'm showing now, we designed a purely learning approach that has its advantages and disadvantages, as I will show now. So basically what we do, we start with images of the scene, and we use a variational autoencoder to learn the representation of the state space of the system. And the system in our case, in this example, is basically states of the shirt that is being folded on the table. So this is basically an overview of this approach. So we start with an image of the scene. We compute a state space representation in the latent space of a variational autoencoder. And using this, and then we build graph-like structure in this latent space that basically just indicates connectivity between different states. So our states are connected by actions, and this map just shows us how we can move between different states. And then we just use it for planning. So, and in this case, planning becomes a simple graph search in this representation. And it looks like this. So we can, as we plan in this graph, in the latent space of a VA, we can show different transitions of how the object should be deformed in order to fulfill the final goal, the folded shirt. Yes, and as I said, this approach is completely data-driven. So we basically train this model on data set that consists of images of the system and actions connecting them. This approach works quite nicely in this example, but there are some challenges, of course, here that were not taken into account. Because this approach is completely data-driven, we're not taking into account what is really a sufficient representation. Because here we kind of rely on a neural network completely in the hope that the network will extract this representation for us. But what if our data is incomplete, for example, or what if some irrelevant factor for the task changes? For example, the background color changes. But the shirt remains the same. So the state really should be the same, but our network will tell us that it's suddenly a completely different state. So here is where we believe that it's important to introduce domain knowledge and, for example, geometric kind of priors, that instead of just paying attention at basically all kind of factors that can appear in the image of this object, we'll only focus on those that are relevant for the task. So in the case of a shirt, we can think of this skeleton or graph that is basically embedded in the shirt, and it represents its configurations so that it has sufficiently much information for the task of folding and unfolding, for example. So then the next question is, how can we define this efficient state representations and how we can extract them from data, how we can learn them, and then how we can use them for planning. Just in the last part of my talk, I will talk a little bit about an example of how this problem can be approached from the geometric point of view. So if we talk about manipulating complex objects and that have some deformability and that are basically being manipulated in 3D, we can think of certain shape features that can help us represent the necessary information about the configuration of an object. So here in this example, if we focus on the objects with narrow parts that have quite different shapes, like for example, it can be this tomatoes or it can be this plant. So what we can notice between all these four images is really that despite their shape differences, they all have this narrow part that we can grasp the object around to basically cage it. And this would be really good because in this case, we can only deal with the smaller representations, only this blue part of the chord, for example, instead of focusing on the entire representation of the object. So this simple shape representation allows us to extract the minimum necessary representation of the state. And similarly here, we can talk about loops or holes in objects that allow us to perform certain classes of manipulation tasks with them. So we can grasp objects using these holes, or we can put them on a hook, or if it's a clothes kind of like object, we can maybe dress a mannequin or a human and put the shirt around the neck and the head of the mannequin, for example. So let's look a bit closer to this. So the narrow passages or the narrow parts here can be formulated mathematically as what we called double forks and necks in this work. So intuitively, it's in the first case, in the case of a double fork, you have a skeleton of an object, and then you extract a part of the skeleton that represents two big branches, here on the top and here on the bottom. And a path that connects these branches. And then this representation is sufficient for various kinds of manipulation. In the case of a neck, it's quite a similar structure. You can think of it as two spheres, basically, that are connected by a path. And I will not go into details here in how we compute them. I will just say basically that the whole pipeline works as follows. So we have some sensory input that comes from cameras. And then we can extract this shape features. And then using the shape features as a minimal state representation, we can perform our manipulation. Another example that uses loops as a shape feature can be seen in this work. So here, we not only work with deformable objects, but we also focus on how their dynamics or how their shape changes as we perform the task. So what's important here is we have, for example, a task of putting this bag on the hook. And we not only want to find the opening in the bag that will allow us to put it on the hook, but we also want to predict how this opening will deform as we perform the task. Because ideally, for manipulation purposes, we would like to keep it wide open to put it on a hook. But because this object is highly deformable, it can happen that the opening will collapse. And to perform this manipulation, to basically have a good control strategy for this object, we need to have some sort of predictive model that will tell us what will happen next to the object. So how the object will deform in the next time step, given a previous history of deformations. And here, we used a purely topological approach to formalize these openings of the objects, so to formalize the shape features and also to extract them. But then, because we also wanted to build a predictive model, we trained a neural network to, given a sequence of observations that predicts how the object will deform in the future. So what we can see here, it's this example of a bag that we're putting on a hook. Here on the left, we have the ground truth, which is basically the two openings that are being detected by our topological algorithm. And they're detected here as triangles. So basically the white triangles are the centers of the two openings. And then on the right here, we have our predictive model that matches these triangles to what the model thinks is the opening of an object. And as we can see, the prediction is quite smooth. And our next step in this work would be to integrate it with a control strategy to use this state representation to perform tasks like hooking or dressing or putting something on a mannequin or something like that. And here, again, just to come back to kind of the main question that I asked in the beginning of my talk, the question is how to find the balance between this purely topological representation that we have here and the learning-based approximation in this case of this topological algorithm. Because one problem that we see on the left is that the purely topological approach is not very robust for topological reasons. So we can see that these triangles are, the motion is not very smooth. So they fluctuate quite a bit around what is really the center of the opening. And we can observe that if we train a neural network on this ground truth data that is extracted using a topological algorithm, this problem is really mitigated because the network provides us with a smoother approximation of the positions of the openings. So that's a big advantage of using learning on top of kind of mathematically sound approximation. Another advantage of combining learning and geometric priors here is that this algorithm that we use to extract the loops completely kind of topologically is really computationally inefficient. And the learned model, in contrast, works in just milliseconds. So this is one of our latest results. And it basically contributes a small step towards answering this big question that I asked at the beginning of my talk, how we can combine priors and domain knowledge and some mathematical sound concepts with learning models. But it's of course just a small step towards this big goal. And the questions in their full generality remain open. So how can we define good state representations that are just enough for the task at hand, but in the same kind of the same time as not just engineered for a task? And how can we use mathematical notions in combination with machine learning to achieve good and reliable results? Okay, thank you very much.